Kia ora, Year 12 and 13. This is the harder part of question 2 from the 2014 complex numbers paper. Alright, I've put this one in small so that we have some room to do the working. It's a locus problem, so we're told that a complex number, z, satisfies this. Right, so this means the modulus of this thing in here is equal to 2. Alright, so let's start by writing let z equal x plus iy. So what we're looking for is x plus iy minus 3 minus 4i equals 2. Now I'm going to go through the mechanics of how we do this in a second, but first let's look at what it's really asking us for, because it will help us see the solution before we do the algebra. So it's saying, tell me all of the combinations of x and y, so all of the points in the complex plane that are 2 units away from this 3 plus 4i. Okay, so just from looking at that, you can see that, well, let's plot 3 plus 4i on the thing. 3 plus 4i is here. So we're looking for all of the points that are 2 units away from that. So obviously that is going to be a circle. Well, I don't know, I think it's obvious, and I'm not very good at spatial reasoning, so it probably really is obvious. There we go. There's a dodgy looking circle. Now we're just going to do the algebra to back that up, but that's the locus of points that you've got to draw. And actually, you can do that straight from the rearranging that we've done. So you don't need to go through all of the algebra to do that. But I'm going to do that anyway, because it might come in handy in some other places. So if you're doing a harder locus problem, what you want to do is to separate the real and the imaginary bits inside the modulus sign. So we're going to get x minus 3 plus I times y minus 4 is equal to 2. So now what I want to do is Pythagoras on both sides. So x minus 3 squared plus y minus 4 squared is equal to 2. I'm going to square both sides and I get x minus 3 squared minus y minus 4 squared is equal to 4, right? Which is what I drew above. It's the equation of a circle which has got its centre at 3 and 4. So for us that's 3 plus 4i, and it's got a radius of 2. And if you're having trouble remembering that, if you think back to when we did conics, the basic form of a circle was this: x squared plus y squared equals r squared. So that's what's going on here. I'm going to fix that circle up because it really is just too terrible. So we'll draw that in slightly more beautifully. Right, so 3 plus 4i, circle. I want to go 2 units out around there. So we'll go out to, where are we? 4 down to 2, up to 6. Here and here. Now we're going to try and do it a bit. There we are. Okay, so there's my circle, and that leads us to the next question, which is what is the maximum value of REZ? Okay, so if you're looking at this, remember this means the real part of my complex number z. So what's the biggest it gets? Well, you can see from looking, it's going to be this value here, which is 5. I'll do that on the next slide. Alright, the maximum value of RE of z, right, so it comes from my circle, so it's this value out here, and it's 5. So if you've got both of those together, that is a merit question. And now we're going to take a look at the excellence question. Okay, so read it carefully first, because you know it's going to have something funky in there. The complex number z is given by this thing here. Right, so z is that, and p and q are real, and p is bigger than q, and they're both positive. Right, this is the important bit that makes it really quite an easy problem if you spot what's going on. Given that arg of z, right, so the angle formed by the x-axis and the complex number is pi on 4, show that P minus 2Q equals 0. But let's think about what it means for the angle to be pi on 4 or 45 degrees. Well, that means that this value, my x value, and my y value must be equal. So I think the best way to do this one is just to start by working with this and then equate the real and the imaginary parts. So z is equal to 1 plus 3i over p plus qi. So multiply top and bottom by the conjugate so that we have a real number in the denominator. Right, so as usual, that denominator will now be p squared plus q squared. Right, if you're not comfortable with that, you need to do some more work on achieve level stuff. Right, but it's our familiar pattern. Up here, the numerator will be p, so I'm doing this one times this one, p plus 3pi minus qi plus 3q, since I squared equals -1. So for arg of z equals pi on 4, we require the real part of z to equal the imaginary part of z. So we need to write something down like that. So let's take a look at what we've got to work with. Well, we don't even have to worry about our denominator because it's the same for both. I'm going to take a new slide to do this though, so that we have a bit more room. Okay, so what have we got? Well, we've got z is equal to p plus 3q plus I times 3p minus q, and that's over p squared plus q squared. So the real part of z is equal to p plus 3q over that. And the imaginary part is equal to 3p minus q, since I've over p squared plus q squared. So if I equate those two things, I get p plus 3q is equal to 3p minus q. And what I'm doing there, of course, is just multiplying everything through by the common denominator. Okay, so there you go. And I'm left with 4q equals 2p, or p minus 2q is equal to 0. Okay, so that's all for now. Hope that made sense. Please let me know if you've got any questions.